Hello everyone, this is Hao from Tencent AI Lab. I'm here to present our paper submitted to ASRU 2023, which is Deep Learning for Joint Acoustic Echo and Acoustic Howling Suppression in Hybrid Meetings. Hybrid meetings are conferencing and collaboration sessions designed to connect in-office employees with distributed workers. It has been increasingly essential in the post-COVID era. Despite the benefits of hybrid meetings, audio-related problems such as acoustic echo and acoustic howling can pose significant challenges and need to be addressed to ensure full duplex communication. The signal model in a hybrid meeting is quite complex. Let's take a simplified hybrid meeting system with only two devices on the same end as an example. As is shown in Figure 1, the foreign speech, denoted as X, is transferred to the two devices on the near end. Since the two devices are not able to tell if they are exposed in the same space, the near end speech S will be picked up by the microphones on both devices and then transferred to both the foreign speaker as well as the other device in the same end. Through this, the microphone signal for device I will be a mixture of target signal SI, background noise NI, and two playback signals. One playback signal is from the device's own loudspeaker to its microphone, and the other one is from the loudspeaker on the other device to the current microphone. Moreover, since the loudspeaker XI is a mixture of foreign speech and signal transmitted from the other device, the microphone signal could be rewritten as this equation, where DJIX and DJIS denotes the playback signal originated from the foreign speech and the near-end speech. It can be seen from Figure 2 that for each device, there are two feedbacks that could lead to acoustic echo and acoustic howling. We treat the feedback signal from the device's own loudspeaker, D11 for device 1, as acoustic echo, as is shown in Figure 2b. Acoustic echo is relatively easier to handle since acoustic echo occurs once per transmission and is handled on both ends. And the device 1 itself has access to the loudspeaker signal X1, which can be used as a reference signal to suppress the playback signal D11. However, the playback signal in the second closed acoustic loop, denoted as D21, is more challenging to suppress due to two reasons. Firstly, device 1 has no access to the reference signal that caused the feedback D21. Secondly, the two devices involved in this closed acoustic loop are exposed in the same space. The challenges we face is to jointly suppress these two playback signals. However, these two playback signals share similar components, and they need to be suppressed jointly. And the presence of either feedback hinders the accurate detection and the elimination of the other, which makes the suppression of both of them challenging. In our proposed method, we employ teacher-forcing training strategy to formulate the joint AEC and AHS task as a general feedback suppression problem, as is detailed in Figure 3. This is based on the assumption that the model, once properly trained, can attenuate all feedback signals and transmit only the target speech S1 through to the other ends. Through teacher-forcing learning, the actual output head of S1 is replaced with a teacher signal S1 during model training. As a result, rather than generated recursively, the microphone signal is simplified to a mixture of target signal, background noise, acoustic echo, and a one-time playback signal determined by S1, as is shown in the second equation on this slide. The network we used for model training is given in Figure 4. It is modified from the network proposed in Citation 1. Our proposed method takes the microphone signal and one or two reference signals, represented as R1 and R2 as inputs, to extract more information from inputs and facilitate the suppression of playback signals. We designed the input feature as a concatenation of the log power spectral correlation metrics across time frame and frequency bins, and channel covariance of input signals. These features are concatenated and then passed through a linear layer for feature fusion, followed by a gated recurrent unit layer and 3 1D convolutional layer to estimate 3 complex value filters. These filters are then applied to the input through deep filtering to obtain the corresponding intermediate signals, denoted as tilde of Y, tilde of R1, and tilde of R2. These signals serve as additional nonlinear reference signal, and their LPS are then concatenated with the original fused features to train in the following part of the network. In the second part of the network, a self-attentive recurrent neural network is employed to estimate a 4-channel enhancement filter, which is then applied on the microphone signal and the 3 learned reference signal to obtain the enhanced target signal head of S1. Finally, an inverse STFT is used to obtain the waveform head of S1. In our studies, based on how many reference signals we used, we have 2 networks denoted as net 2 channel and net 3 channel, where net 3 channel is depicted in figure 4, and net 2 channel is a simplified version of it, where we removed all the branches connected to tilde of R2 in the network. Our loss function is defined as a combined loss of SISDR, mean absolute value, and the proposed correlation loss. Experiments are carried out using ASRU and Interspeech 2021 AEC challenge data. We considered variations in terms of RIR, system delay, and SPR-SNR during model training. Performance of the proposed method is evaluated using SISDR and PASC. We first investigate the impact of input and reference signal configurations on model performance. To diminish the influence of model size difference during this comparison, we use net 2 channel to train inputs with either 1 or 2 reference signals. For the cases with 2 reference signals, as shown in the last 2 rows of the table, the sequence of reference signal determines from which reference signal the intermediate signal tilde of R1 is obtained from. It is seen that the results presented in the last row, where we have X21 for calculating tilde of R1 and X only serving as an additional input for feature fusion, achieves the highest overall performance among the tested configurations. Table 2 compares the performance of models trained with net 2 channel, input of Y1, X1, and loss 2 calculated using different playback signals. The results show that incorporating the correlation loss does not always lead to performance improvement, while using loss 2 calculated based on D21 achieved the best performance and outperforms the model trained using loss 1, especially in terms of SISDR. We combine the findings and made through exploration regarding inputs and loss function and train a model to achieve the best feedback suppression performance. The results are shown in this slide. The performance comparison results presented in Table 3 demonstrate that using net 3 channel results in better performance than using net 2 channel, and employing the modified loss function, which is loss 2, could further improve playback attenuation performance. This slide shows the conclusions and future work. We have proposed a deep learning-based method for addressing audio-related problems in hybrid meetings. Our proposed method treats acoustic echo and acoustic howling as integrated feedback problem and achieves simultaneous AEC and AHS using a teacher-first learning strategy. The impact of input signal and loss functions on joint AEC and AHS performance has been investigated. Future work includes investigating streaming inference performance under real hybrid meeting setup, while considering practical issues such as computational complexity. That's all for the presentation. Thank you.